Right, so this doesn't work. Apparently it does. I didn't plan on proving you wrong. That was purely accidental. Okay, so I'm an analysis grunt at Leap Australia. I'm based in that one. Whereas something doesn't work. There we go. The Melbourne dot. So we're basically software resellers, but we do a huge amount of consulting, and technical support and training and mentoring is a huge part of what we do. So that's how David roped me into this. So he wrangled me into working on this project with him. So this is just a bit about Leap. ANSYS is the main software package that I work with. It's basically the finite element analysis, CFD, electromagnetics, all the simulation stuff. We also do a lot of CAD stuff with PTC and a whole bunch of other stuff. And LSTC, which has been purchased by ANSYS as of 2019. So that's basically LS-DYNA. So I'll be talking all about LS-DYNA in this presentation. Right, so this block of text, basically I'm saying that what we were doing in this project was developing a modeling strategy for efficient and accurate investigative process. So humans are expensive and simulation's expensive. So we want to get as much done as possible in these simulations, and wasting a lot of time developing simulation models is not very productive. So we've been working together to try and simulate heart valves in as efficient way as possible. So we've got to identify and utilize appropriate simplifications for the analysis and automate it as much as possible. So David and his group has been really good at that. I've basically done the model development stage, getting things working, handed it over to David, taught them how to do it, and then they've written Python scripts and done all sorts of great work to automate this process and make it much more efficient. And then the eventual goal is to develop a digital twin of all of this work. And Irene will be talking about that afterwards. So I should give you a little bit of background about LS-DYNA, because we'll be talking about it a lot. So it's 3 years older than me. It started life in 1976. This guy, John Holquist, started writing it as an academic. And it was developed initially as a code to simulate some of the impact behavior in nuclear blasts. So he worked on that for a while. There was a 2D version and a 3D version. He released the source code in 1978. So it's more or less open source. But automotive and defense and a lot of other organizations were really interested in the capability. So eventually, in 1988, LSTC was formed and it became a commercial code. And he's been developing it ever since. So he's a very ambitious guy. He wants LS-DYNA to be all things to all people, hence all the capability that I'll be showing you shortly. So this is kind of what it is. LS-DYNA itself is just a single executable, but it does all of this stuff. And the main capability is this thing here, explicit finite element analysis. Basically, it's vehicle crash simulations, blast, projectile impacts, all that sort of stuff. So that's its bread and butter. It has all this other capability as well. ICFD, which I'll be showing you, that's an incompressible CFD code. It can do a lot of chemistry. It's got particle methods for discrete element modeling and also brittle fracture with SPH and other methods. It can do NVH and acoustics. It's also got an implicit static FEA code. It can do electromagnetics, and I'll be hinting at that as well. This new thing called isogeometric analysis for automotive sheet metal forming and crash and stuff, thermal analysis, and a compressible high Mach number CFD code. It's also got these other things, optimization. LS pre-post is a pre and post processing tool. LS task, which listening to some of the other presentations, I thought this actually could be kind of useful because it's an optimization and topology and shape optimization tool. So you could use it for optimizing thickness distribution in a heart valve leaflet based on simulation results. So I only sort of thought about that while watching some of the other presentations. So it's late afternoon. So I've got lots of animations and colorful pictures to keep people interested. I figure that's probably the only way it's going to work. So these are some of the things LS-DYNA is used for. Product design, that's opening and closing a clip. It's actually a very tricky thing to simulate. LS-DYNA does it very easily. It has a lot of airbag modeling capability for simulating airbags in vehicle crash. So that can be used in biomedical stuff as well, stents and other things. Slinkies, very important research area, and pushing people downstairs. So this thing to work. Oh, no, sorry, back. Maybe you're right about this. Some of the other, let's just go back. This time for sure. Okay, cool. So this is ALE. Its text is hidden behind the top bar, but it stands for arbitrary Lagrangian Eulerian, and it's kind of a hybrid analysis approach. The Lagrangian is the standard finite element explicit code that we use for all the vehicle crash simulation stuff. ALE is, the Eulerian is more akin to CFD or fluid flow analysis. So arbitrary Lagrangian Eulerian means we're combining the two. So we can do things like this here. Make sure I hit the right button. This guy, top right-hand corner, that is an IED blast under a defense vehicle. And you can see the impact and what it does to that guy's legs. This will often break shin bones. This is some sloshing simulation. And this is a simulation of that blast that happened in Beirut. So it has quite a diverse range of capability. And as is often the case, a lot of this development is paid for by defense and sporting organizations and all that sort of stuff, people with deep pockets, which is great because then we can come along and jury rig all of this technology into simulating heart valves, which is basically what we've done. So this is the sort of range of simulation capability that we look at. So down here in this end, we have creep and static and dynamic. And so basically small strain, very slow things. And then we have the other end of the scale where we have ballistics, maybe a drop impact simulation, ballistics, detonation and blast, and right up the other end, hypervelocity impact, like particles hitting the James Webb Space Telescope. Basically everything behaves as a liquid, even metal at these sorts of velocities. So very challenging things to simulate. So we have implicit FEA and explicit FEA. So explicit handles all of that sort of stuff, all the difficult stuff on the right-hand side. We have a bit of a crossover here, and this is kind of where we live with heart valve simulation. We could use either explicit methods or implicit methods. And just one more example, which is really fairly exciting for what you guys are doing. This is a ventricle, and it's a three-way coupled simulation. And two-way coupled simulations get analysts very excited, but this is three-way coupled. So what it is it's electrophysiology. So we're simulating the electrical wave moving up through the heart valve. That triggers the muscle tissue, which is the structural side. And then that affects the fluid, which is inside. So we have electrophysiology, structural, and fluid all coupled together in one simulation. And then right up the top, we have a little heart valve. So that's opening. And then down here, we have a pacemaker. So we can see how all the fluid flow is affecting the pacemaker, how the pacemaker affects all of that. So that's really quite a cool simulation. Doing all of that sort of stuff is probably overkill for designing just the heart valve itself. We really just want to know what the fluid boundary conditions are and then just work on the heart valve. But down the track, you can do all of this sort of stuff too. You could couple this to a thermal solver as well and make it four-way coupled if you're just showing off. Okay, in LS-DYNA, there are about 300 odd constitutive material models just for modeling different things like soil, concrete, metals, all that sort of stuff. And it has a lot of specialty materials just developed for this sort of problem. So soft tissue for ligaments, tendons, etc. Heart tissue, lung tissue, mat muscle, which is for simulating contraction of muscles, brain tissue, and this one here, which is mat tissue dispersed, which is specifically for heart valve sorry, not heart valve, but heart muscle simulation. And what you see down here is the Toyota thumbs model, which is a dummy model developed by Toyota for crash simulation. And it's an improvement on the hybrid 3 dummies that have been used traditionally, which are basically simulation models of hybrid 3 dummies, whereas this is a simulation model of an actual human. So you can see all the various bits of tissue and bone and everything like that. So you can have injury criteria based on the state of the lungs and the heart and the brain and all that sort of stuff. So they're very clever and sophisticated. Okay, so what we're doing is heart valves. So we've broken it down into 3 basic stages to try and eliminate as many variables as possible early on and minimize the amount of hard work we have to do later. So the easiest stuff to do is a pure structural simulation, and we can do this in ANSYS Mechanical. This is the ANSYS Mechanical environment. It's all associated with geometry. You can change the geometry very quickly, click update, and it remeshes, reapplies your boundary conditions, solves it, and gives you your results in a flash. Very easy to do. Problem with this is, actually, I'll tell you about the problems in the next slide. And this one here is the next level of complexity up, where we're using that ALE technology, which is developed for BLAST. So this is the ALE domain, which I've cut through so you can kind of see the valve embedded in it. And then this one here is the throw the kitchen sink in ICFD fluid structure interaction model, which is the most difficult one to set up, takes the longest to solve, but gives you the best results. So phase 1 is the pure structural analysis. So the pros of this is it's really easy to set up. Set it up in a flash, it solves very quickly. This one solved in 3 minutes on my laptop. You can do quick validation of materials. You can do a bit of sanity checking to see where stress concentrations are, all that sort of stuff. Make sure it's basically behaving as you'd expect it. So you can eliminate garbage designs very quickly. Also, the user learning curve is very fast. So you can teach someone to do that very quickly. Cons are, if you're applying, to load this, we're applying a pressure directly to the surface of these shell elements. And a pressure load in finite element analysis is always normal to the surface. So as the valve opens up, the pressure is still normal to the surface, whereas in reality, the fluid is flowing past the surface. So the loading is no longer really realistic. It's not representative. So that's a big shortcoming. You have no information on the fluid behavior, flow rates, pressure, turbulence, streamlines, all of that sort of stuff. So you get none of the interesting fluid structure interaction. You can get interesting things like this. This is something David did, and we scratched our heads working out why we're getting different results between the LS-DYNA explicit dynamic simulation and the ANSYS implicit transient simulation. Explicit by its very nature captures a lot of vibration and oscillation, and we thought this was a problem in the model until we did a modal analysis and looked at it and sort of zoomed in to see what was going on, and there was actually some sort of oscillation behavior in the valve. So it was realistic. This is a real thing that we're getting up there. The implicit finite element solver missed it. So by its nature, explicit analysis captures this detail that we just weren't expecting. This is the ALE model, phase 2. So this is the the Eulerian domain, and then the valve is embedded in it. I'll be explaining how this works in the next couple of slides. Pros are, gives you basic FSI behavior. It's not perfect, but it gives you very good information. The fluid pressure loading on the valve is much more realistic than just a pressure load on the surface of the shell elements. You get flow rate, pressure, you can get streamlines, as you can see there. So nice looking animations to put in presentations. The fluid and the structural meshes are completely independent. As you can see here, they're just one's embedded in the other. So if you want to change the valve shape, it's very easy. You just change the geometry, update the mesh, done. You don't have to worry about updating the flow domain. That can remain as it was. So that makes life a lot easier. You can get realistic valve closure behavior, and we've managed to set this up in ANSYS Workbench using a whole bunch of command snippets. So the workflow is very efficient. So we've automated a lot of that process. On its own, ANSYS Workbench can't do the simulation, but you can do a lot of trickery with command snippets and name selections and stuff to get it to do what we want. Downside is it takes 4 to 8 hours to solve on 32 cores. It's a bit of a steeper learning curve to learn how to do an ALE simulation. You don't capture boundary layer effects on this, so it's not like a full fat CFD analysis. So you miss all of that sort of detail. You don't get turbulence effects. The flow domain, as you can see here, must be meshed with hexahedral elements. So if you want complex geometry representing sort of complex curved walls of the valve and the blood vessel, it's much more difficult to achieve. And you can get some fluid leakage, although I don't think that's what's going on here. We think that's a post-processing artifact, but we're not really too concerned about it. Then this is phase 3. So this is the full FSI. So this is all tetrahedral elements, which is really great because it's easy to mesh a complex domain with tetrahedral elements. So you can have any arbitrary shaped domain representing the blood vessel. It gives us full two-way FSI. It gives you complete information about the valve opening, flow, turbulence behavior, fluid stresses, all that sort of stuff. Yeah, downside takes about 40 hours to solve on 48 cores. So if you want these pretty pictures, you have to pay for them. So we want to eliminate all of the garbage designs before we put all the effort into this. It's also a very steep learning curve, learning how to do this. I had to learn how to do it, to do this, and then I had to teach them how to do it, and a lot of hair was pulled. The structural mesh and the fluid mesh are connected. So if you want to change one, you have to change both, and you have to regenerate both the meshes. So a bit of extra work there, but David's been very clever, and he wrote Python script to basically automate the conversion of what ANSYS Workbench spits out and convert it into what LS-DYNA needs to do a CFD analysis. So while I was sitting there like an idiot editing text files, typing things and deleting things, David wrote a Python script and just took my job away. So that's much better. But yeah, you get these, you can get all this nice behavior here where we've got the flow changing direction, get some fluttering happening, and then closing again. Also, one thing I should mention is a bit of a trigger, probably a trigger warning. These valves are all using linear, isotropic, homogeneous material models. So all that fancy material science you've been talking about all day, none of that is here. That's just the most boring, simple material model you can imagine. But it's what we use to get a basic model working. This flies now, we know it works. Now we can go to town. Sina's going to come to me and he's going to say, how do I do this crazy stuff in the valve with, weird distributions of thickness and reinforcement here and there. And then, we go back to work and we work out how to do that. And then we'll get much more realistic behavior. Like you can see where the valve closes, there's kind of a gap in the middle. That's not realistic. That's because in bending, this is too stiff because it's a linear elastic material model, whereas a hyperelastic material model wouldn't do that. So yeah, as I said, trigger warning for the material scientists. So how does ALE work? So these are the ALE elements. They're a multi-material element. So each of those elements can have multiple materials inside it at once, and the material flows through the mesh. Mesh is static, material flows through it like a CFD. We have a flow-in domain, or a pressure inlet, and then a pressure outlet. This LS-DYNA wasn't developed for doing heart valve simulations, so we had to jury rig a polynomial equation of state for defining the pressure in the material, and use the internal energy per unit reference volume, basically a history curve, which defines that to initialize the pressure of the fluid, which comes in here. That's why we have the separate body here. And once we worked that out, it was easy. So now we can have a transient initial pressure at the inlet, and that gives you your flow, which is great. We have no slip boundary condition on the outside. And then the coupling is basically the interaction between the Eulerian elements and the structural elements. So that's where the pressure from the fluid is applied to the Lagrangian elements there. And then the Lagrangian elements provide a barrier for the fluid. So the fluid can't flow past that barrier presented by those shell elements. And we call that coupling. And that's the LS-DYNA keyword that makes that work. This is what Euler ALE looks like under the hood. So if you imagine a finite element mesh like that, we have some material inside it. Something happens, mesh deforms, material deforms. It deforms into that, just like a normal finite element simulation. And this happens over a single execution time step. But then we have an additional advection cycle where we take the new location for the material from the deformed mesh and we advect it back onto the original mesh. So now we have the material in the new location, but on the original mesh. And we repeat that every single computational cycle. So the mesh stays static and the material moves through it. So that's what's happening behind the curtain. When we look at it, it just looks like normal CFD, but it's more akin to finite element analysis, where you have a deforming mesh. We're just doing this extra step where we advect the material back onto the undeformed mesh. And you can see that happening here. So here's a thing impacting a plate, and the material flows through the mesh. And that's what it would look like if it was purely Lagrangian. So Lagrangian finite element mesh impacting a plate. So this is the computational cycle. Over one time step, you calculate the strain rates. From the strain rates, you can calculate the stresses. From the material properties and the stresses, you can calculate the nodal forces. And then from the nodal forces, the contact forces, all the other forces that are involved, you can compute all the kinematics of what's going on. And normally that's where the loop ends and you just repeat that. But with ALE, we have this extra advection step where we take that result and then map everything back onto the undeformed mesh. So that's ALE in a nutshell. And this is what it looks like when you try to make something that doesn't want to do ALE. So this would be our normal mechanical model. And then we've got all of these LS-DYNA keywords here stuffed into a command snippet. And that gives us all the extra capability. So once we had worked all of that out, it's great. We can just change the geometry. We can, if we want to do a new valve design, modify the valve, update the mesh, hit solve, and it'll do it all automatically. So that makes life a lot easier. How am I doing for time? And this is what it looks like from the multi-material perspective. So this is the inlet fluid pushing through, and you can see it pushes through the valve there and then comes out the other side. This is all just the same liquid, which for our purposes is just water for now. They appear to be separate materials because we have an inlet fluid, we have the initial fluid, and then we have an outlet fluid, which we use for tracking mass flow rate, those sorts of things. But that's basically ALE doing its thing. So here's some velocity streamlines, as I promised, some pretty animations. That's outlet mass flow rate, so we can track that at the outlet. That was surprisingly difficult to get. David and I spent a long time trying to work out how to do this because it naturally doesn't want to, but we worked out how to get the mass flow rate at the outlet, which is a very important parameter. Reversing the flow. So that's an important thing. And you can quickly see that, maybe this valve is not so great because you can see it sort of folding over and twisting. So that's a deformation contour plot, and that's a stress contour plot. So this is the FSI model. So as I said, it's an incompressible fluid behavior, so low Mach numbers. It can be treated as a standalone CFD solver, or it can be loosely coupled to the explicit finite element code. So loosely coupled means you're basically just transferring data in one direction. You don't have the two codes passing displacements and pressures back and forth. We're doing strongly coupled, which is the CFD solver strongly coupled to the implicit LS-DYNA finite element solver, but it's all under the same executable. So that gives us the most accurate interaction between the two domains. We have to generate a surface mesh in the ANSYS Workbench tool, and then we feed this surface mesh into David's Python code. That spits out stuff that we can basically feed straight into the LS-DYNA solver. And then when you hit solve, it generates the volume mesh. So unlike most CFD codes where you spend a lot of time generating a volume mesh and creating your boundary layers, that's all done at runtime. So you just give it a surface mesh, hit solve, and it creates the mesh and then runs with it. So a few more animations. That's the valve von Mises stress, the flow velocity, and then the pressure. So you can see this going through the full cycle of blowing through and then reversing. And there's our dirty little gap that we're ashamed of. We had some leakage up here due to the way the mesh pinches off, and it was a known problem, and there's a fix in it now, so ignore that. We fixed it. The developers are aware of it, and it's working now. And there it's opening again. Right, so the next steps, better material models. So we need to take everything everyone said earlier today and then integrate that into an accurate material model for the next step. And that'll be a combination of things like fancy hyperelastic material models, orthotropic material models, also localized reinforcement. So we might want to have truss elements which represent some sort of reinforcement embedded in the shell elements representing the valve. And we basically just move those around until we get the valve to behave as we want. So there's lots of tactics we can use to get the simulation valve behaving as we want. So yeah, orthotropic materials, rib stiffening features, all that sort of stuff. Next stage then after that is building a digital twin, which I won't talk about. I'm not going to step on feet. And then there's also some work on developing valves that can adapt to growth using models that determine the opening behavior. So as the valves get bigger, we want the same valve to be able to work without having to keep replacing the valve, which is an unpleasant process, I'm told. Yeah, so that's me. Thanks.